Hello YouTube. Today I would like to show you how you can calculate the delayed Lenz effect on a regenerative acceleration generator. So this is a follow-up video on my earlier video about the Heinz regenerative acceleration generator replication. So today I would show you how you can calculate the delayed Lenz effect. So there we go. In a normal inductor, you can see that when you provide a DC voltage to it, that the inductor will respond on this by creating a magnetic field, and the creation of the magnetic field follows this graph. So at 1 L over R times, or L divided by R times, the magnetic field has expanded to 63.2% of its maximum field strength. So, and at 5 L over R times you can see that it have reached its maximum, and it's 100%. So, and when you remove the DC voltage from it, then you see the opposite effect taking place, so that in 1 L over R times you would expect that the magnetic field is diminished to, let's say, 36.8%, and that in 5 L over R times the total magnetic field is gone. So this is the normal reaction which you can expect when you try to hook a DC voltage to a normal inductor, and at the second part you can see what you would expect when you try to remove it from the normal DC voltage. So what we've done in the regenerative generator example, in the regenerative acceleration generator example, is that we do the exact opposite. So then we introduce a magnet, so that all of a sudden there is a magnetic field and all of a sudden it is gone. But in this generator this action goes so fast that the high impedance coil isn't able to create its back EMF fast enough. So in this graph you can see that in 1 L over R times it is at 63.2%, but when you increase L, then you can see that the total time constant value is also increased. So now I would like to do some calculation. For now, when we try to calculate values from a normal generator, what I've done is that I have measured two values of one coil of our 500 watt 240 volt generator, and this generator has got a generator coil of 106 millihenries, and it's got an internal resistance of 21.1 ohms. So in this schematic, this is the coil, here's the internal resistance, and here's the load. When you try to calculate the time constant for this, you can see that the time constant is L divided by R total, R total, so R internal plus the R load. So when, for instance, you try to hook up a 200 ohms load to it, then you can fill in the parameters, and you can see that it will take you 0.4794 milliseconds for the generator coil to create its back EMF to 63.2%. So this is really fast, and this is when in normal generators you can see that it's pretty easy to introduce rotor drag because this value is low. So now let's do the same for the regenerative acceleration generator example. What I have done is, for those two values, I've used exactly the same values as which you can see earlier in my regenerative acceleration generator replication video. So for now it is 2.182 henries, and my generator coil has an internal resistance of 384.5 ohms. So when you try to hook up the same load to this, the same 200 ohms load resistance, you can see that you get a total different time constant value of it. So this value is much bigger than in the previous low current coil, low impedance, high current low impedance coil. So in this case it's now 3.7 milliseconds, and you can see that with this high impedance coil this value is almost 10 times bigger than in the previous high current coil. So this is the time constant value 0.4794 milliseconds for a normal generator coil, high current, low voltage, and for the regenerative generator coil, high voltage and high impedance, you can see that this value is almost 10 times as big. So this is what we are looking for, because when this value is big, the back EMF of the generator coil isn't fast enough to create rotor drag, but instead of it, when this value is high enough and your rotor frequency is high enough, then it will create acceleration instead of rotor drag, and that is what we are looking for. Now, one more thing, what I have also done is that I have did the same calculation for the regenerative acceleration generator, also at 2.182 henries and 384.5 ohms of internal resistance, but now in case of a shorting. So here you can see that now it is short circuit, that there is introduced now a short circuit to the regenerative acceleration generator coil, and in this case you can see that the value, the normal time constant, is even bigger than the 3.7 milliseconds which you saw in the normal in the load example. So you can see that one more time, the regenerative acceleration generator under load will create a 3.73 milliseconds time constant, and when you short it, the time constant is then you will get an even bigger time constant. So here you can see that this time constant is directly in relation with what we saw earlier in my previous videos, so that when you try to short the regenerative generator high impedance coil, that the acceleration effect takes place at lower frequencies, and that when you try to do the same thing for a normal load connected to it, that the value is slightly smaller, so that you will need a higher frequency to get the same effect. So compare one more time, when we compare the normal generator coil, high current, low impedance, you can see that this time constant value is really small, so the back EMF is developing really fast. So you can see that in normal generators there's introduced rotor drag really fast, and that in the regenerative acceleration setup, this value almost is 10 times as big, the time constant value, so that you can see that with fast rotor RPM or frequency, generator frequency, you can see that when you compare the frequency time constant with this time constant, that you can see that you would be able to create regenerative acceleration. Okay, that was it for today. Thanks for watching. Bye bye.